morning, friends. I welcome you all here for my course, Engineering Thermodynamics. Till now, I have completed the basic concept of thermodynamics, some basic definitions, properties of substances, work and heat, and also I have done the first law of thermodynamics in my previous class. We have seen till now the intensive properties like pressure, temperature, specific volume, and internal energy we have seen in the last class during the discussion of the first law of thermodynamics. Today we are going to see further two very important thermodynamic properties, that is the enthalpy and the specific heat. This I am going to cover by the help of the first law of thermodynamics. So here if you see, in today's class I am going to discuss about constant pressure equilibrium process of a simple compressible substances, enthalpy of a simple compressible substances, specific heats of pure substances, specific heats of pure substances at constant volume, specific heats of pure substances at constant pressure, observation of specific heat. In this observation we will see that how the Cp and the Cv, their relations, these things I am going to discuss in my next slides. So if you see here that first I will discuss about constant pressure equilibrium process of a simple compressible substance. So here we can see that constant pressure equilibrium process of a simple compressible substance. So what is the meaning of the simple compressible substance? Is that substance in which only the mechanical work, that is PdV, is only considered. That type of system is called the simple compressible substances. So in that only the volume change is there. So the work done will be the PdV. So in this case we can see that if Q is the heat supplied to a system so that the piston moves slowly upward, as the reference pressure does not change, so the inside pressure will not change. Let us write the first law of thermodynamics. So here we can see that this is the cylinder and this is the piston and here is the system. So if the Q is heat supplied to a system, so if I supply a Q here, so the piston start moving from here. Assume it has reached to new position here. This is the new position of the piston. So your volume, this is the V1 and now this is the V2. So V2 minus V1 is a net change in the volume. And we are taking it as a quasi equilibrium condition in which the resistance force and the applied force will be in equilibrium condition. So Q is the heat supplied here to the piston and it moves slowly upward. At the reference pressure does not change, so the inside pressure will not change. So here pressure will remain constant because it is a very, very slow process and it is called the quasi equilibrium condition. So the pressure from the upside and the pressure from the downside both will remain the constant and they will balance the system. So let us write the first law of thermodynamics for a given system. So if it is the Q and the work is transferred out, so here we will see that del Q from position 1 to position 2. So this del Q, that is heat supplied from the position 1 in this diagram to the position 2 will be the summation of the differential integration from 1 to 2 dE plus 1 to 2 del W. Here we can write that del Q is equal to Q12, but dE, it is exact differential, so this is E2 minus E1 plus del dW 1 to 2 is W12. If change in kinetic and the potential energy is negligible, means delta PE comma delta KE both are negligible. If both are negligible, then E2 minus E1 is equal to U2 minus U1, because only this is the internal energy. So E is equal to U plus kinetic energy plus potential energy. So these things we assume as a negligible, 0. So this delta E here is equal to delta U. So here we will get Q12 is equal to E2 minus E1 plus W12. So for E2 minus E1, we can write here U2 minus U1 for the simple compressible substances. Here kinetic energy and the potential energy is negligible, and we are assuming that these things are 0. So we got here the heat supplied is equal to change in internal energy plus work done. The system is simple compressible substance, then pressure P will remain the constant. We are assuming that from 1 to 2 it is only P, not P1 and the P2. So the work done W12 here, this work done is equal to 1 to 2 integration P dV. P is a constant, so P will be outside, and this dV will be V2 minus V1. So work done, we got that P into V2 minus V1. As P1 is equal to P2 is equal to constant, because we have here given constant pressure equilibrium, means we remain the equilibrium, that is called the quasi-equilibrium system. In that, pressure will remain constant. So P1 is equal to P2 is equal to, due to constant pressure process. So we can write that PV2 minus V1, we can write P2V2 minus P1V1. Now if you see that Q12 is equal to U2 minus U1 plus P2V2 minus P1V1. Now this U2 and P2V2 in one bracket if we can keep, and U1 and P1V1 in another bracket. So U2 plus P2V2 minus U1 plus P1V1. We know that U plus PdV as PV and U are the property. So this is also, if you see here in that U, P and V, all are the intensive property. So, and this, the summation of U2 plus P2 into V2 is another property, and this is called the enthalpy, H. So here H is equal to U plus PV. This is a new property which we have got. Till now we have seen the pressure, temperature, specific volume, internal energy U. Now this is the fifth one, that is the H, that is the enthalpy. So enthalpy also we got one intensive property. So what is the enthalpy? Enthalpy is the summation of the internal energy plus work done. So enthalpy is a property of a pure simple compressible substance and is valid for all processes. So actually here we have derived this thing with the help of a constant pressure process. But in the real scene, this equation you can use for any processes, and this will be valid for all type of process. So here we can write that Q12 is equal to U2 plus P2V2 minus U1 plus P1V1, and this is equal to H2 minus H1. It means difference in enthalpy, means whatever heat you are supplying, this will be the difference of enthalpy of the system. We can write in a specific form, and this you know that specific form will be in the small letters, small case. So we can write the specific formed by dividing by mass. So here this we can write is small h is equal to capital H by m. So here we can write the U by m plus P capital V by m. So small u plus P into small v. So this enthalpy or specific enthalpy, small h is equal to internal energy, specific internal energy plus pressure into specific value. So this is the your property. So we have got another property, that is the specific enthalpy, and like a specific value, a specific enthalpy also given in the steam table and different tables of the systems like water table, ammonia table, refrigerant table, everywhere this H will be given. So we can also find out this H by the help of, if you know the U and the PV, you can find out. If not given, you can find out. Or if H is given, PV is given, you can find out the U by the help of the tables. Tables are available. In that you can get U, P, V, H, T. So these properties we have 1, 2, 3, 4 and 5. They are the extensive property. Intensive property we have got. So as of now we are aware about these 5 properties. So in the last class we have discussed about internal energy, that is also the property. As of now we got these many properties. Further we will be discussing some more. So what is the enthalpy? So if you want to define the enthalpy, so enthalpy, the sum of the internal energy and the product of the pressure and the volume of a thermodynamic system. So here just you can see sum of the internal energy plus pressure P into volume of the thermodynamic system. It is also the measurement of the energy in a thermodynamic system. So it is a measurement of the total energy in any thermodynamic system, and it is denoted by the enthalpy. Now, specific heats of substance by first law of thermodynamics. So this we have derived this internal energy also U by the help of the first law of thermodynamics. We have also now have got the enthalpy by the help of the first law of thermodynamics. So from the first law of thermodynamics, we are getting these parameters or the properties. So start with algebraic example, then we will bring out the physics of the specific heat. So here we will start with the mathematics. From the mathematics, we will find out the specific heat, and how this we have got this we will be discussing in this next topic. So now internal energy of a substance is a property. U is a property we have seen. Property is a unique function of the state point. So for a particular state point, suppose if this is the point 1. So here if you see it is a TV diagram. So it is a T1 and V1. It is a specific. If it is the point 2, T2 into V2. So like this, the properties will be specific for a given point, and they are unique. So property is a unique function of the state point. The state point can be ascertained by a specified 2 independent intensive properties. Here just you can see that T and V I am showing here. So this T and V are the 2 properties. By these 2 properties we can ascertain the system of this thing. The state point can be ascertained by specified 2 independent intensive properties. Let us take temperature and specific volume as 2 independent intensive property as specified in the state. It is, I have shown here that T and V. is the specific properties. So this we can see here that suppose this internal energy, this U is a internal energy U is equal to U into U and the function of T and the specific temperature and specific value. If you take this derivatives of U, so du is equal to del U by del T when V is a constant into dt plus del U by del V when T is a constant into dV. So the total this differential is equal to summation of each variables. So total differentiation is the summation of its partial derivatives. We give a definition. So here very much we can see that. So del U by del T when the V is a constant into dt plus del U by del V when T is a constant. So in this one we will make the constant, another we will make the vary. So if we make this summation, we will get the total differentiation and the total value of U. So now if you see here, this part is what? This is the del U by del T when V is a constant. So this is called specific heat at a constant value. So here what happened? V is a constant and here change in internal energy with change in time. This definition is governed by mathematical expression as del U by del T is a property, as del U is a property and del T is a property. So both are the property. So their ratio is also property, and this ratio del U by del T is also called the specific heat. And it is denoted by C. So we will just discuss about first specific heat at constant value. So we have find out that the ratio of the internal energy to the ratio of the temperature is called the specific heat. Specific heat we have the two types. One is specific heat at the constant volume, another is the specific heat at a constant pressure. We will be discussing here first the specific heat at constant value. So here we have find out just now that Cv is equal to del U by del T when the volume is constant is called the specific heat at a constant value. Here U is varied with the T. U is varied with this internal energy is varied with the T temperature. The state point, the Cv will be unique for any, like U is unique, T is unique, same way the specific volume at constant volume will be unique. We have derived this with a constant volume, but this equation is valid for all processes you follow. So this specific volume at constant, specific heat at constant volume is valid for any processes, not only the constant value. Once property is evaluated, it is not depend on the constant volume process. Once you find out the value of the Cv, it will remain for all type of all processes. Imagine at constant volume process, del V is equal to 0. So we have shown that del U is equal to du is equal to del U by del T V dt plus del U by del V T. So here into del V. So here for the constant volume, the change in volume is 0. So this term is 0. So here we got that du is equal to del U by del T when V is a constant into dt, and this is called the Cv. So now this du is equal to del U by del T into dt, and this is called CV. So this du is equal to CV dt. Applying the first law of thermodynamics, now del Q is equal to du plus del W. Del W for the constant volume, del W is equal to 0 as dV is equal to 0. So dQ is equal to del U, and del U is equal to du is equal to CV delta T, and this into M. So M CV delta T. So we got this dQ is equal to, so del Q is equal to M CV and dt. So this we got. From where we can find out this CV. So what is the definition of this CV? So CV is equal to del Q by del T into 1 by M. So this is the formula for the specific volume. So we can see here that CV is equal to 1 by M del Q by del T. So this is the specific volume. So we can define from here the specific volume. So what is the specific volume? The specific heat at a constant volume, that is CV, is defined as the quantity of heat. This is the quantity of heat required to raise the temperature of unit mass of the gas by 1 degree. So what is the specific heat? Specific heat is defined as the quantity of heat. This del Q is a quantity of heat required to raise the temperature of a unit mass to 1 degree when it is heated at a constant volume. So here it is a constant volume. It is given by the symbol CV. So in this way, now we can go for the physics. From mathematics, we have find out that CV is equal to 1 by M del Q by del T. Now we can understand the physics behind that, and we can define in the physics pattern that the specific heat of a gas at a constant volume CV is defined as the quantity of heat required to raise the temperature of unit mass of the gas by 1 degree when it is heated at a constant volume. So this we can see here. So it is very easy to define from here itself. So it is a quantity of heat dQ required to raise a temperature of 1 degree for a unit mass of a substance. So that is the definition of the specific heat at a constant volume, and it should be at a constant volume. Now the next part is specific heat at constant pressure. So let us take an example by choosing enthalpy as a property. So now there we have taken as a internal energy, but here we will take the enthalpy H as a property. H is a function of temperature and the pressure. So this H is equal to function of temperature and pressure. Assuming temperature and pressure, it is a temperature T and the pressure are independent property. So this can be only independent. This is not applicable for two-phase region, as in this the temperature T and the P are dependent to each other. So if you know that this is the two-phase region, so from here, P and T are in the same, they are dependent each other. But if you go in this region or in this region, they are not dependent. Okay, so we have to take care that this process should happen either this side or that side. It should not be in the two-phase of region. So this is not applicable for two-phase region, as this T and P are dependent to each other. So this is not applicable for two-phase region, as in this T and P are dependent to each other. So H is equal to the function of T and P. So this dH is equal to del H by del T, del H by del T into dt plus del H by del P when temperature is constant, dP is equal to 0. Here we have to see that it is in the constant pressure process. So this dP will be 0. So dH by dt here, dH by dt when P is a constant is called the specific heat at a constant pressure, and that is called the Cp. So this dH by dt, there it was du by dt. Here it is dH by dt and H is a enthalpy. So del H by del T when P is a constant is called the specific heat at a constant pressure. We know that at constant pressure, quasi-equilibrium, del Q is equal to del H. We have seen that this supplied heat is equal to change in enthalpy. So we can write that Cp is equal to 1 by, in place of dH, we can write dQ. So 1 by m dQ by dt when pressure is constant. So we got the specific value, specific heat at constant pressure is equal to 1 by m dQ by del T when pressure is constant. Now I will again, like our previous about specific heat at constant volume, that is Cv, we have defined by this mathematics. Same way we are going to define this thing in the next slide. So this is the equation for the Cp, that Cp is equal to 1 by del Q by del T when P is constant. Now I will define the specific heat at constant pressure, that is the Cp. So the specific heat of a gas at constant pressure is defined. So here I will write here Cp is equal to 1 by m del Q by del T when P is constant. So this we have derived in the previous slide, that Cp is equal to 1 by m del Q by del T when P is a constant. So the specific heat, this is the specific heat at a constant pressure, is defined as the heat, as the quantity of heat required to raise the temperature of unit mass of a gas by 1 degree. The pressure remain constant, this P is a constant during the process, during the heating. It is given by the symbol Cp. So here this Cp, it is a quantity of heat required to raise the temperature of unit mass of a gas by 1 degree when the pressure remained constant. Now we have find out the Cv, that is the specific heat at constant volume and specific heat at constant pressure. Now we have to see that what is the relation between the Cp and the Cv and how these things are varying for different type of gases, for different types of substances. So this is, I am writing here observation, and this observation we will see physics behind that, and same time these things we can also see in this only by the help of the mathematics, and we can derive the relation between Cv and the Cp. So the first observation is Cp is always greater than Cv. That is the first observation, that Cp is greater than Cv. The specific heat at constant pressure is greater than the specific heat at constant volume. So why? So during the constant pressure process, volume change is taking place. The heat is required more than the constant volume process, as in this no volume change and no work is done in constant volume process. But in constant pressure process, work is also done. Greater heat supplied needed in constant pressure. So just I will show you here that what is the meaning of Cp and the Cv. So this is the piston and this is the cylinder, and here is your system. Here we have supplied some heat here, Q. So if it is a constant volume process, piston will not move. It will remain here. But if it is a constant pressure process, piston will move. So work will be done. So from here it has moved to here. So the volume change, it is V2 and this is the V1. So there is a change in volume at constant pressure P. So work done 1 to 2 is equal to P V2 minus V1. So in this, the heat supply, specific heat is Cp. So in this case, Cp will be greater than the Cv, because in Cv no work is done. There is no change in volume. Volume will remain constant. So work will not be done. But in the constant pressure process, work will be also the heat supplied. This heat will be changing to the internal energy and plus work will be done. So the first law is saying that del Q is equal to du plus del W. So here work is done and some heat is absorbed. So here the Cp is greater than Cv. So this is the clarification for the Cp is greater than Cv, and the reason I have mentioned that in the constant pressure process there is a change in specific volume, but in a constant volume, the volume is constant, work done is 0. Now the second observation, I will see that this Cp and Cv will be different for the different types of gases. So we have the monoatomic gases, we have the diatomic gases, we have the polyatomic gases. So for the different types of gases, the values of Cp and Cv will be different, and this also depend upon their temperature intensity. So first I am going to discuss about monoatomic gases like helium and argon. Only translational motion of molecules are present. Only translational motion of molecules are present. Cp and Cv are virtually independent of the temperature and remains constant. So in this, what happened? If it is monoatomic gases, so the motion will be only one direction. Molecules will move like this, or from here to here, or from here to here. Okay. So the only translational motion of molecules are present in monoatomic gases. In this case, Cp and Cv are virtually independent of the temperature and remains constant. So in this case, they are independent of the temperature, and mostly Cv and Cp both will remain constant if they are the monoatomic gases. That is the first case. The second case, if you see, for the diatomic gases like hydrogen, oxygen, nitrogen, carbon dioxide, etc., in this, vibrations of the molecules are present. So if these molecules, it will vibrate like this, like this, like this, and it will also go the linear. So the both things will be there. Vibration plus linear motion will be there. So molecules are present. In this, Cp and Cv are more dependent on temperature than the monoatomic. Okay, Cp and Cv are more dependent on temperature than the monoatomic, but not severely as polyatomic. Means for monoatomic, they are not dependent at all. But in this diatomic, they are very much dependent on the temperature. Okay, so Cp and Cv are not constant, but they are dependent on the temperature. If you see the third type of gases, they are the polyatomic, like carbon dioxide, ammonia, sulfur dioxide, and so many other gases are there. Here, not only the linear vibration, but also rotatory motion will be there. In this, linear motion, vibrations, and rotation of the molecules will be there. So here the Cp and Cv are severely dependent on temperature. So temperature is key parameter. Temperature is key parameter for these gases. So if we are studying the polyatomic gases, thermodynamics of the polyatomic gases, temperature is very, very important. As you increase or decrease the temperature, the value of Cp and Cv will also be increasing or decreasing as per the application of the temperature. Now the third observation, for ideal gases, the Cp and Cv are dependent on temperature only. So Cp and Cv are the function of the temperature, not any other properties. So the Cp and Cv are the function of temperature for the any ideal gases. This was proved by an experiment by the Joule, discussed in the next slide. So how for ideal gas, the Joule has conducted the experiment, and that experiment gave very good concept that how the Cp and Cv are only dependent on the temperature, not anything else. So here I am going to show the Joule experiment. Joule has taken a hot water bath in which two glass bulbs, one with air and another is kept in vacuum. Both bulbs are connected with a on-off valve. When valve was open, it's a free expansion and work done is 0. Also, there is no change in temperature, so heat is also 0. So we can use this first law of this thermodynamics. Okay, so this we can see here. This is the Joule experiment. There is a chamber. This is the chamber here, from here to here. Inside we have the two bulbs. One bulb is filled with some pressurized air. Another bulb is with a vacuum. This is the hot water. Here is a thermometer. This is the thermometer. Bulb of air, bulb of the vacuum. Here is the hot water bath. And here is a valve. This valve, if you open, this air will go from here to this side. And all of a sudden, if you open, there will be a free expansion. And we know that if you have the free expansion, work will not be done. So here the objective for this experiment is that if we expand this, whether this temperature will increase or the decrease. So after this thing also, he found that temperature has not increased. So when the valve was open, it's a free expansion and work done is 0. Also there is no change in the temperature, so heat is also 0. So he has observed that in this condition, when he opened this valve and he has measured this bath temperature, there is no change in the temperature also. So del Q is also 0. So by the first law of the thermodynamics, del Q is equal to du plus del W. Here del W is equal to 0 as it is a free expansion in the vacuum, and del Q is equal to 0 as there is no change in the temperature in this. So here we can find out that du is equal to 0, means net change in internal energy is equal to 0. So this internal energy U is the function of temperature only. So that we were discussing in the previous, that it is Cp and the Cv, they are the function of the temperature. Same way, the internal energy is the function of the temperature only. So here we will see for the relation between the Cp and the Cv for the ideal gas. So for the ideal gas, we will write that Cv is equal to is Cv not indicates for ideal gas, and the Cp is equal to Cp naught is taken. We know that Cv naught is equal to du by dt and Cp naught is equal to dh by dt. We have seen in the previous. So Cp naught minus Cv naught, d of dt, h minus u. We know that h is equal to u plus pv. So small h is equal to small u plus p into small v. So h minus u is equal to p into v. So here h minus u we can write p into v. So d of dt, this is a small t, capital T, it is temperature. It is PV. So d of dt, PV is equal to RT. So we have write RT, and if you differentiate this, T will be 1, and so this Cp naught minus Cv naught is equal to R. So Cp minus Cv is equal to R. This is for the ideal gas. So this is the relation between Cp and the Cv, and Cp naught minus Cv naught for ideal gas, Cp minus Cv is equal to R. This is the relation which we have got. So as of now, we have covered we have find out the enthalpy by the help of the first law of thermodynamics. These are coming as a corollaries of the first law of thermodynamics. We have find out the H enthalpy, and this H is equal to U plus PV. Another, we have got the specific heat at constant volume CV, and this CV is equal to 1 by m dq by dt when volume is constant, and Cp is equal to 1 by m dq by dt when pressure is constant. And the relation between Cp and the Cv, the Cp is greater than the Cv, and Cp minus Cv is equal to R. So this R is a gas constant. So this we have find out. In my next class, I will be discussing about the numericals. I will be going for the 2 numericals. Numerical problem 1 related to the first law of thermodynamics, finding the state point, work and heat. Numerical problem number 2 related to the first law of thermodynamics to find the heat transfer. Numerical problem number 3 related to the first law of thermodynamics to find the final pressure and the temperature. These are the references for my lectures, that is P.K. Nog in Engineering Thermodynamics, Tata McGraw-Hill's, Eunice Sengel, Michael A. Ball's Thermodynamics and Engineering Approach, Tata McGraw-Hill's, and this is the lecture from NPTEL by Professor Mishra from IIT Kanpur, and also Professor Suman from IIT Kharagpur. I am thankful for these 2 professors. I have listened their lectures and I have tried to do something from there. Any questions, you are welcome to ask. I have my email ydwivedi@gmail.com. Please like, subscribe and give comment on my YouTube channel to boost my morale. I will feel very happy if you are liking my lecture. Thank you very much for the joining. Please do wait for my next lecture in this. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.